Contact stresses are present whenever two objects exert a force upon one another. The force causes both objects to deform and creates a stress distribution beneath the surface of both objects. While there are numerous examples of this in the real world, this video will be focusing on finding the von Mises stress distribution caused by the contact between a train's wheel and its track, given the necessary material properties and physical dimensions. The first step to finding the contact stresses between a train's wheel and its track is to find the size of this deformation. This can be done by using the first equation below. In this equation, r refers to the radius of the body, E is the Young's modulus, nu is the Poisson's ratio, P is the applied load, L is the length of the area of contact, and A is the half-width of the area of contact. In this case, subscript 1 will be associated with the wheel, while subscript 2 will be associated with the track. By making the simplifying assumption that the wheel can be idealized as a cylinder, and treating the track as a cylinder with an infinitely large radius, the half-width of the contact area can be calculated by using the second formula. Once this is found, the maximum contact pressure can then be found by using the third equation. Now that the maximum contact pressure is known, the principal stresses can then be determined as a function of the depth below the center of the area of contact by using these three equations. For the third principal stress, use the Poisson's ratio of the track. These principal stresses can then be used to find the von Mises stress distribution by using the equation below. With the theoretical stress distribution found, it is now necessary to use finite element analysis to simulate this loading condition and validate these results. In finite element analysis, this problem can be simplified by collapsing the 3D geometry into a two-dimensional problem, utilizing symmetry across the vertical axis. On top of this, only the bottom half of the wheel needs to be modeled, as the top half of the wheel is not of interest to this problem. From here, it becomes necessary to define the area of contact between the two bodies and further specify these edges as no separation contact. In order to properly mesh the geometry, there was extensive mesh refinement along the surfaces of contact between both the wheel and the track. This refinement was done 4 layers deep in order to correctly capture the stress distribution beneath the surface of both bodies. A distributed load was then applied along the top surface of the wheel, with half the magnitude of the load in the problem statement due to the symmetry condition being utilized. Due to the large size of the wheel, any differences between defining it as a distributed load instead of a point load will be negligible and make convergence of the results much easier. In terms of boundary conditions, horizontal displacement was fixed along the axis of symmetry, and the bottom of the track body was made to be a fixed support. In order to validate the analytical and computer-simulated findings, the following setup was chosen. A hydraulic press will be used to apply a distributed load upon a half cylinder of 1065 steel that is positioned atop a sample of train track that has had its top surface milled flat. A strain gauge will then be placed along the side of the track, flush with its top surface and centered with the area of contact. Due to the large size of the wheel used in both the stress analysis theory and in the finite element analysis, practicality dictates that a smaller wheel be used. In this case, the half wheel will have half the diameter of the wheel previously used, but maintain its original width. This would affect the overall stress distribution, but by also halving the magnitude of the load, the magnitude of the stress distribution will be maintained, but the area of contact will be halved. When the test is run and the load is applied to the half wheel, the strain will be measured, and by using the pictured formula, it can be converted into a displacement. This measured displacement can then be compared to the displacement found in the finite element analysis. With both the theoretical data and the finite element analysis data found, it now becomes necessary to analyze the findings of these two methods. By looking at the von Mises stress distribution, it is possible to see a definite shape characterized by an initial dip in the stress in the system, followed by the peak stress occurring approximately when the depth divided by the half area of contact is equal to approximately 0.74. These findings have been backed by previously done analyses and research papers, such as the findings of Darji and Vicaria, pictured on the right. These results were marginally replicated in the finite element analysis results. By using the probe tool within ANSYS, it became possible to extract the values of the von Mises stress along the axis of symmetry. By plotting these extracted values, it is possible to see that the computer simulation gives a stress distribution that has a shape similar to that of the analytical results. The issue, though, is the magnitude of the stress found by the finite element analysis was 2 orders of magnitude lower than that found by analytical means. This discrepancy came from an issue with the contact area, which caused a discontinuity that created an area of high stress that would not normally be present in the system in real life. So in conclusion, the shape of the stress distribution of the theoretical results and of the finite element analysis are in very good agreement. On the other hand, the magnitudes of the stresses are very different, which is likely due to issues that arose while ANSYS solved the computer simulation. Unfortunately, solving these issues is beyond the scope of this class and would be better suited for a class on advanced finite element analysis. Thank you for watching this video on contact stresses.